Hi, this is a short presentation for the poster 147, excitation of San Andreas tremors by thermal instabilities below the seismogenic zone, from Sylvain Barbot and Yifeng Wang. So we have strong observations of seismic activity at the deep extension of the San Andreas fault northwest of Parkfield that have been closely associated very recently with slow slip events from analysis of geodetic data. These observations strongly challenge our assumptions about the rheology of the continental crust because this seismic and slow slip activity takes place in regions that we typically associate with velocity strengthening behavior that would prevent any mechanical instabilities. So no slow slip, no tremor. And we owe this understanding of the rheology of the crust by some laboratory experiments on wet samples that indicate velocity weakening behavior between 50 and 350 degrees Celsius, which we associate with the seismogenic zone. And the same laboratory observations indicate temperature weakening behavior at greater temperature. And if temperature is allowed to vary dynamically because of shear heating, this may provide a mechanism for the generation of slow slip and tremors. But this in a mathematical framework, we build a constitutive framework that allows a rate and state and temperature dependence of friction that allows us to keep track of the feedbacks between shear heating and frictional resistance. So we write the friction and shear stress as a function of normal stress, velocity, state variable, and temperature through an Arrhenius relationship. Healing is also allowed to be thoroughly activated through an Arrhenius law. And at steady state, the frictional resistance depends on velocity and temperature with some coefficients. So A minus B controls the velocity dependence of friction at steady state, and AQ minus BH controls the temperature dependence of friction. So temperature weakening is obtained at AQ minus BH positive. Last, to represent shear heating and diffusion, we use a membrane diffusion equation where the temperature is increased by shear heating and diffused away along the characteristic wavelength. That's the size of the shear zone. When we put these equations together, they form a closed form constitutive framework, and under some conditions, it creates slow slip events, limit cycles that repeat perpetually with temperature raising all the way to 1,000 degrees, meaning that it's close to the solidus of wet granite under these conditions. So it is possible that thermal instabilities can create slow slip and generate enough heat to create melting of the rocks. We can model the same under a three-dimensional setting to model these observations at Parkfield more precisely. So we create a velocity strengthening region in the mid-crust, but also temperature weakening and a narrow region that is unstable. That is, in this region, shear heating is very efficient. When we do that, we can reproduce the duration and recurrence time statistics of low-frequency earthquakes in this region, and all the events have scaling between duration and moment that resembles what is observed in nature, with a broad range of events between linear and cubic scaling. The slow slip events occur between every few months and are associated with a temperature increase. And at very few isolated locations along the fault, the temperature reaches the solidus of wet granite. So we interpret this as that the slow slip events may be associated with high temperature proxies, such as the presence of pseudotachylytes in exposed fault zones.